Today on How It's Made. Pressure cookers. Mechanical singing birds. Oceanographic buoys. And stainless steel tank trailers. When the pressure is on, the juices start flowing for quick results. The pressure cooker traps steam inside to raise the cooking temperature and produce a meal in minutes. The technology has been around for centuries, but was only adapted for household use in the 1930s, when the concept really picked up steam. Modern pressure cookers have new lid locking technology and safety features, keeping it on the front burner in the kitchen gadget department. A pressure cooker starts with this stainless steel disc. A dip of some lubricant will aid the forming process as equipment pushes the disc over a pot-shaped die. That flat disc is now a nicely rounded pot. Next, this punch cutter moves in to make notches in the pot's rim. These notches will interlock with the pressure cooker lid, allowing it to hold up tight against steam pressure. Next, they submerge aluminum discs in a liquid mix of aluminum and silicon to give them an even coating. While the disc is still damp, they arrange it on the bottom of the pot, then set a stainless steel disc on top of it. A turntable delivers the pot to an element that's heated to more than 1100 degrees Fahrenheit. This intense heat activates the aluminum and silicon solution to fuse the discs to the bottom of the pot. Then it's into a cooling tank where the pots float towards the next station. There, two blades shave away the ragged edges of the fused layers on the bottom of the pot. It creates a cosmetic beveled effect. That layer of aluminum sandwiched between the steel will improve the pot's heat conductivity. And now it's time for some grit and polish. In this special chamber, sanding and buffing tools add luster to the pots. The pressure cooker pot then takes a trip through a washing station to clean off the sanding residue. And now it's ready for the crowning touch, the lid. It takes 6 pressing operations to shape it completely. The holes at the center are for the pressure cooker's 2 safety valves. To install the main valve, they align a retaining ring with the lid's larger hole, then pop the spring valve into that hole. An automated device underneath tightly screws it into place. The backup valve goes in the smaller hole. These 2 valves are crucial. They'll release excess steam to avert an explosion. A rubber ring creates an airtight seal with the pot. They test the valves and check the sealing ring, along with the lid's closing mechanism. This plastic cooking guide encircles the main safety valve, but doesn't impede its function. They weld several bolts into the pot on either side. They leave a bit of space between the bolt heads and the pot. This allows them to install the brackets for the handles. They torque the bolts to tightly secure the bracketed handles. After all, a pressure cooker is one thing you don't want to lose your grip on. And now this pressure cooker is in the home stretch. There's one last test, which they perform on randomly selected pots. They pump the pot full of air to simulate the effect of steam and confirm that this pot can handle the pressure. Pressure cookers with double walls are another innovation. They'll keep that stew warm longer to ease the pressure on the chef. Mechanical singing birds first appeared in 1780, adorning snuff boxes. The Swiss-made novelty soon became the rage among classy Europeans. A few decades later, a French watchmaker perfected the sound mechanism, making the birdsong virtually indiscernible from the real thing. Switzerland is home to the last remaining company making these singing automatons. The workshop crafts large ones that go in bird cages and small ones that pop out of boxes and clock cases. The first step is to adjust the bird's two spring-loaded steel rods. One pivots the bird's head, and the other its beak and tail. Then it's time to dress the bird's body. It's illegal to harvest real bird feathers, so the artist uses real antique feathers in a couple of key spots, and realistic-looking synthetic feathers everywhere else. To craft the tail, she glues feathers onto stiff paper, then folds it over and adheres it to the bird. Then she adds more feathers, meticulously creating colorful layers. The plumage alone takes about 4 hours' work. No two birds are alike. Each is a unique piece of art. In the technical department, they screw the wind-up key to the mechanical movement that animates the birds. The movement is made up of 250 brass and steel components, assembled manually. They connect leather bellows. The movement pumps the bellows, which sends air through a tiny whistle producing the bird song. Now for the birdie. This one's the small pop-up kind that goes in a box or clock case. They screw him to a lever in the movement. Then, using a brass template, position him correctly. This rack gear moves the bird from side to side while he's up and singing. This pin attaches that gear to the movement. This lever pops the bird out of his nest, moves the rack gear, and pumps the bellows. A push button on the movement triggers the lever, setting all this in motion. Now they install the movement into its decorative box. Bird cage models require an identical but larger movement. The base of the cage sits on top of it. The rods that manipulate the birds connect to the movement through tubes and brass perches. Workers construct the top of the cage over a curved form. First, they slide on 2 brass rings and position a brass disc at the top. Then they feed thick brass wire through holes in the rings. They lock each wire onto the disc temporarily. Then, with a bit of acid to help the process, solder the wires to the disc permanently. After making sure everything's well positioned, they solder the wires to the rings as well. Once the structure is soldered, the cage can safely come off the form. Decorative brass rings cover the structural ones. They too have to be soldered in place. This requires a light brush of acid, lead pellets, and a torch to melt the lead, bonding the outer and inner rings. Every mechanical singing bird this company produces is a work of artistic and technical craftsmanship that delivers a performance on command. Oceanographic buoys enable scientists to study the sea, help meteorologists predict weather, and rescue teams better define a search area. The top part of the buoy houses instrumentation that tracks temperature, surface currents, and other conditions. Its antenna transmits the data via satellite to a base station. This model has a ball-shaped surface float with a tether cable connecting a long fabric tube called a drogue. The drogue detects water movement several yards below the surface. The component that connects the surface float to the cable is called the stress relief. The factory makes this part in a mold, casting 10 at a time. Workers inject liquid urethane into the mold cavities. It's the same material from which inline skate wheels are made. After 3 hours, they extract the castings, which then cure for a full week. The surface float contains a barometer sensor that collects air pressure data, as well as a temperature sensor and a locating system. A 13.5-volt battery pack powers all these instruments. Workers build it by arranging 36 standard D-cell batteries. Using nickel strips, they make pairs, linking a negative end to a positive end. Then they spot weld the strips, creating circuit pathways along which electricity will flow. Next, they immobilize the batteries by filling the spaces between them with hot glue. Then they weld the final connections and solder on the leads that'll connect the battery pack to the instrumentation. Now they apply special insulating paper to prevent the battery pack from shorting, should it come into contact with a metal object. A wide band of electrical tape safely seals this 13-pound battery pack. The nylon polypropylene drogue is too lightweight to hang vertically in the water, so it needs something to weigh it down. That something is a heavy plastic hoop. They make the hoop by blowing sand into a plastic garden hose. The sand makes it heavy. After capping the hose, they insert it in a pocket at the bottom of the drogue. So now the drogue, all 26 feet of it, will dangle straight down into the water. Now for that stress relief they molded earlier on. It attaches underneath the bottom half of the surface float. Inside the bottom half, they install the battery pack, then a control board, a transmitter, and an antenna. The surface float is made of ABS plastic. The top surface coated for UV protection because it will be exposed to direct sunlight. They attach one end of the tether cable to the stress relief and the other end to the drogue. They reinforce the connection with epoxy. This type of buoy is designed to monitor only the top yard of water, so it doesn't have a long vertical drogue like the other one. What it does have is a parachute, because it's designed to be dropped by aircraft in a search and rescue operation to mark the location of an incident. As the demonstration shows, the buoy opens on impact. All the components are spring-loaded, floats made of foam, drogues around a central cylinder housing the instrumentation, and on top, an antenna. The buoy packaging is water-soluble and biodegradable, so over time it simply disintegrates. No need to retrieve them. Stainless steel tank trailers carry all kinds of products, from milk, sugar, and animal feed to fertilizer, shampoo, or even wine. Some tank trailers only haul chemicals like methanol. Made of stainless steel inside and out, they keep all the products they're transporting contaminant-free. Stainless steel tank trailers carry as much as 12,000 gallons of product. They start with a laser cutting machine, which cuts pieces like this manhole opening from the stainless steel sheet used to make the tank. The laser that cuts the steel is as precise as the pen you use to sign your name. Next, they make the larger pieces of the tank by putting 2 sheets of stainless steel into a machine called a plasma seam welder. Using stainless steel wire as a filler metal, the computer-controlled machine welds the 2 sheets of steel together. A worker then uses a belt sander that rides on a track to smooth out the weld evenly and in a straight line. The sheet then goes through a rolling machine that shapes it into a cylinder. It takes 2 to 4 cylinders to make a tank, depending on the size. Meanwhile, a ring rolling machine makes what's called channel rings that will strengthen the cylinders and help them keep their round shape. The rings are also made of corrosion-resistant stainless steel. Some tanks need up to 12 of these reinforcement rings. A worker then welds the channel rings onto the tank, stopping periodically to inspect the weld. Next, they weld tank heads to the cylinder. Welding parts on the outside of the tank causes heat discoloration to the steel on the inside. That's why a worker then polishes the stainless steel, giving the full interior of the tank a noticeably clean and bright finish. Then they attach polyurethane spacer bands to the tank. These create the sections they need to mount fiberglass insulation around the tank, which keeps the product either warm or cold. Workers then install thin sections of stainless steel around the tank to protect the insulation. This steel is shiny for cosmetic reasons only. They hold the sections in place temporarily using leather belts. They secure this entire outer wrapper so it fits properly. Then they weld each section of steel to the frame of the tank. Next, they prepare the outer wrapper heads using what's called a lock seam flanger. That makes a lip in the edge of the heads. They attach the front and rear heads to the outer wrapper by fitting the lip into the outer wrapper's grooved edge and crimping them together using a hammer. Next, they install the aluminum fenders over the rear tires. After that, they attach a stainless steel tube ladder that gives access to the manhole at the top of the tank, where they load the product. They put the mud guards on next, followed by the reflective conspicuity tape that goes on both sides of the tank and on the two rear bumpers. They install the stoplights and taillights into a light box at the rear of the trailer. After that, they install the turn indicators on the sides of the trailer and test them to ensure they function properly. Finally, they check all the connections used to operate the tank trailer, so when it leaves the plant, it works perfectly, and the customer can transport their product safely.